Hi folks, this is Matt Ingram continuing the replication of Baller et al. In R. I've covered already some preliminaries here about the fact that I don't assume any prior knowledge of R and a reference to Anselin's text on spatial regression analysis in R. I've also discussed in previous videos that I assume that you've downloaded and installed R and that you've already gained some basic familiarity with the syntax and working in the R environment. Excuse me. And then lastly, this slide orients us to where we are in the replication. We've already covered essentially the first half, the first large bullet, the main bullet point, and then the first part of the replication items in the bottom half of this slide. I'm going to start here with table 1, the OLS regression. So let's go straight to R. Here we are in our familiar R environment, and I'm in step 8, the OLS model. This is the syntax for the OLS model. You're essentially using this command linear model. Again, you could use the help command to find out more about this particular command if you wanted to look up the syntax or if you had forgotten the syntax. And we're going to create this regression or this object nat60.lm using the linear model command. So let's do that. I'm just going to hit Control R to execute. You can see that it executed successfully on the left here, and now we can summarize that object. And here are our regression results. We can compare these quickly to table 1 in Baller et al. If we just look at the first line, resource deprivation 1960, and compare that to Baller et al., we see that the coefficient 1.798 matches exactly the coefficient in Baller et al., and the significance is also the same. So in R, excuse me, we could execute that command to generate the regression object and then summarize it. You could also use this shorthand where you're essentially combining both commands into a single line. You're summarizing what's inside the parentheses, and inside the parentheses you've created your linear model object. So that's one way you could shorthand this into a single line of code. You could also generate a separate object with the summary of your regression object. If we do that, we see that it's executed correctly, and then we could export that summary object as a CSV file. We could export it as a Word document or as a text file. I'm not going to execute these right now. They're just there for your own information. So that's the simple least squares regression of the 1960 data from table 1. A couple of exercises that you could do on your own is to replicate the same analysis, the same least squares model for 1970, 1980, and 1990. Once you've done all 4 models, you could use this code to combine all of the output into a single table, and basically you'd be creating 4 different objects using the data that you've outputted using the commands above, and then create a new object with all of that data, and then capture that object, that combined object, as a CSV file. So let's move on to the diagnostics that Baller et al. Use to lead them down the path of doing the spatial regimes analysis. There's a few different diagnostics here that I've included, some spatial, some non-spatial, but let's focus on the spatial ones. First, one cool visual diagnostic that is not included in Baller et al., but that I just wanted to demonstrate here is a plot of the Moran's eye and its significance over various orders of spatial lags from Roger Bivan. I'm going to execute this command right now just so we can look at it quickly, and then we'll talk about it. It's going to take a little bit, so I might just pause for a second. Here we are again. Let's see what this object created, or what this command created. And let's plot it. It's this visualization that I think you'll find interesting. Basically, in the first order spatial lags, that first order of neighbors, we've calculated this Moran's I for the data. If we use the second order of neighbors, we calculate this Moran's I. Again, this is the data for the on the residuals of the OLS object we just ran in the least squares regression. So this is how much spatial autocorrelation is left in the residuals after our OLS object, indicating that least squares is not. We shouldn't stop with just a least squares regression. There's substantial interdependence or dependence among our units of observation. The spatial autocorrelation in the residuals drops, but is still statistically significant at the second order of neighbors, and it continues through the fifth order of neighbors. It doesn't become non-significant until the sixth or seventh order of neighbors, and then interestingly becomes there's a little bit of statistically significant spatial autocorrelation at the eighth order of neighbors. So this is an interesting visualization of the spatial diagnostic of detecting the spatial autocorrelation in the residuals after an OLS regression. Of course, the test that they employ is the spatial Chow test. Here is a basic non-version of the Chow test in case you do not have any spatial autocorrelation in your errors. So if there is no spatial autocorrelation, you could use this Chow test to see if maybe there's a different relationship across different regions or regimes. You would execute it with this code here, all the way down to here. However, returning to the spatial diagnostics, again, this first plot helps us see to what extent there's spatial autocorrelation in the residuals over various orders of neighbors, but the more formal test is the Lagrange multiplier series of tests. Very basic command is this one. This one generates only the Lagrange multiplier error test. We could also repeat this Moran's test over here from this plot from Roger Bevand. We could do it just for the first order of neighbors. I'm just going to hit Control R here. You'll see it executing over here on the left. So it generates a statistic of 0.112 basically, and you'll see that that matches this first plot here on the top left. It's about 0.112 at the first order of neighbors. That's the same thing you've just calculated here. But the full test of Lagrange multiplier tests, or the full complete set of these tests, is down here. So if you execute this command, you're essentially asking R to run the Lagrange multiplier tests on your OLS object, on this OLS object, using this spatial weights matrix. This is our row standardized spatial weights matrix. And then you're asking it to run these tests. So the basic Lagrange multiplier error model, the robust version of that test, the basic Lagrange multiplier lag test, and then the robust version of that test, and then a mixed test. So let's run this and see what the results are. And Control R. You can see it executing on the left, and we have our results. So we go up to the top, and here's our full set of tests. Here's the basic error test and the robust test. Remember from the reading that we want to look first at both basic tests, so the basic error test and then the basic lag tests. Both are very large and statistically significant, so we move to the robust version of both tests. In the robust version of both tests, here and here, we see that the size has dropped dramatically for the robust version of the error test, and it is no longer statistically significant. The lag test has also dropped, but is still quite large and remains statistically significant. This is our first indication that maybe there's more of a spatial lag process, more of a diffusion process going on in the outcome of interest than a spatial error process. However, the mixed test is also statistically significant. So there's some indication here that there's a combination of processes going on, and this is one of the things that leads Baller et al. Down the path of thinking about maybe different spatial processes going on in different regions of US counties. So let's go through with the formal spatial chow test now, which is their sort of final test, In R, following Anselin's instructions from his 2007 manual, you would specify an unrestrained model. That is one model that's allowing the coefficients to vary across regions, across the south and the north and the non-south, the two, this dummy variable that we've created above. If you want details on how we created it, it's right here. We first had to attach the data frame from the national data set. We created a new, I'll just run this right now. In this data frame, we created a new variable called non-south. That was basically the opposite of south, 1 minus south, since south was is a dummy variable, 0, 1. And then we created a new constant combining both of them, and we added these variables to the data frame. If we summarize that data frame, as you can see, it now includes these two new variables. So again, going down to the spatial chow test, we want to run an unrestrained model allowing the coefficients to vary across both regimes, and then run a restrained model that is constraining the coefficients, not allowing them to vary, making them fixed across both regions. So we can run both of these models. So now we've run the two models, and here are the results of the two models. We'd like to look at the the unrestrained model, just to glance quickly at the interactions between our predictors of interest and the region dummies. So it's this set of results here that can be helpful in identifying non-stationary coefficients, that is, coefficients that vary across different regions. So here we look at resource deprivation, and we see that across both the south and the non-south, the effect is positive and statistically significant, so not too much there. Population structure across the south and non-south also positive, but not statistically significant across both regions. So there's an interesting variation across regions. Median age is negative across both regions and also statistically significant. Divorce positive and statistically significant, and then unemployment is negative and statistically significant in the south and slightly positive but not really statistically significant, at least not at the standard 0.05 cutoff in the non-south. So there's two variables that indicate some non-stationarity or some spatial heterogeneity. That is, that the effect of the coefficients, whether it's the magnitude or their statistical significance or their direction, varies across these two regions. And we can go back to the code, and this is the code for the more formal spatial chow test. Again, we're looking the null test. If it's not significant, it would indicate that the coefficients are the same or stationary or fixed across the two regions. If it's large and statistically significant, then the coefficients vary across the two regions. So we'll just hit run here, and we see here the result. This is the coefficient and its statistical significance, and it is both large and statistically significant. So again, you're printing the chow test and its p-value, the chow test and its p-value, and then a degrees of freedom the degrees of freedom is the third variable. But these are the two outputs that we're most concerned about. Again, this indicates that we can reject the null hypothesis of coefficient stability. The coefficients appear to be unstable across the two regimes, again motivating the spatial regimes approach taken by Baller et al. So I'll stop there, as now that motivates the spatial regimes approach, and we can then move on to the spatial lag and spatial error regressions across the two regimes. Thank you.